Hello everyone, welcome back to part 3 of our lecture on chapter 5, the discrete time Fourier transform. In this lecture, which will be a fairly short lecture, we're going to look at a couple of very important topics, the frequency response and the convolution property. So let's start with a little bit of review here, and this will show us the relationship between the Fourier transform and the frequency response of a system. So recall from chapter 3 that if we have an impulse delta function going into a discrete time LTI system, then the output of the system we call h of n, which is the impulse response. Likewise, if we have for our input of the system a frequency component that is represented by the complex exponential e to the j omega n, then what the system outputs is that same frequency component, e to the j omega n, but it's now modified by this function h of j omega, which is the frequency response. And furthermore, we saw in chapter 3 that h of j omega was related to h of n, which remember is the impulse response, by this summation here. But what we just learned in this chapter is that this summation here is the definition of a Fourier transform of this sequence h of n in here. So here we come to an important conclusion here, that the frequency response is just the Fourier transform of the impulse response. So this is why we use the lowercase h for h of n for the impulse response, and we use uppercase h for the frequency response, because remember our rule here is whatever in the time domain, whatever letter we use for our sequence, in this case h, we make it an uppercase letter here in the frequency domain. So this is the relationship, the important relationship between frequency response and impulse response. They are related by the Fourier transform. Let's take a look at the convolution property. And again, this is going to mirror exactly what we did in chapter 4. So this is the convolution property for the discrete time Fourier transform, just like we did the continuous time Fourier transform in chapter 4. So in the time domain, we have our standard diagram here is, here's our system. We send an input sequence x of n into the system. Then the output of the system is given by the convolution of x of n and the impulse response h of n. And here again, this symbol, this asterisk or star symbol, means convolution. Take the convolution of these two. If we go to the frequency domain by using the Fourier transform, then little x of n becomes big X of j omega. The output, y of n, becomes y of j omega. So this is the Fourier transform of the output. But look at the Fourier transform output. It's given by the product of x and h, not the convolution like we had to do in time, but just a simple multiplication of the transform of x and the transform of h. And by the way, h, remember, is called the frequency response. So this is the convolution property. It basically says that if, in the time domain, we have to do a convolution, then in the frequency domain, all we have to do is a simple multiplication. So in general, if we have in the time domain some sequence A convolution with some sequence B, then in the frequency domain, we take the Fourier transform to get big A multiplied by big B. So convolution in the time domain results in simple multiplication in the frequency domain. And again, this is of course a very, very welcome result, because you remember from chapter 2, especially the homework, how tedious and complicated convolutions can be. So now we have a very nifty way to sort of circumvent the need to do convolutions. We can just sort of go around and go to the frequency domain and avoid convolutions altogether. Here's an informal proof of the convolution property, and again, this is the same one that I basically showed in chapter 4, so I'm going to skip over this for now. One thing I will mention here, because we will see this later in the course, is this convolution and multiplication property dualism. And so basically what it says is that the convolution property says that if we have convolution in the time domain, we have multiplication in the frequency domain. All right, but sort of the converse of this is what your textbook calls the multiplication property. If we have multiplication of two signals or sequences in the time domain, then we actually have to do a convolution of their transforms in the frequency domain. So this is something that we're not going to have to deal with in this chapter, but we will use these properties here, especially this multiplication property. It's going to become important when we get to sampling theory in Chapter 7 and our introduction to communication system theory in Chapter 8. But for now, we're going to focus on the convolution property for the remainder of this chapter. So here's one application of the convolution property, and again, this is similar to what we did in Chapter 4. If we have two systems in cascade architecture or series architecture, in other words, we have one subsystem here called System 1, and it's connected to subsystem 2 here. And so System 1 has an impulse response h of 1, System 2 has an impulse response h of 2. Then the output of this whole thing, it's basically, you know, whatever this input signal is here, x, convolution with h1, convolution with h2. All right, so obviously this would be, you know, a real nightmare to try to figure out because you'd have to do two convolutions here to find the output. But by going, you know, using the convolution property, what we can do here, and you know, I won't go through all the intermediate steps here, but basically you can think of System 1 has a frequency response h of 1, all right, big H, and System 2 has a frequency response h of 2. Well, now when we, you know, since we're in the frequency domain, we can just multiply these two frequency responses together. We don't have to do convolution like we saw up here. So we can combine these two subsystems into a single system that has a resulting frequency response given by h1 of j omega times h2 of j omega. All right, there's no convolution needed here. Furthermore, we can take this thing one step further. Obviously, since this is multiplication, and multiplication, you know, is commutative, h1 times h2 is the same as h2 times h1. So the order that we write these doesn't matter at all because it's just multiplication anyway. So we can, if we write h2 first and then h1, we can split this system back apart. And now notice we have subsystem 2 before subsystem 1, and this is exactly equivalent to this right here, where System 1 was first and System 2 was last. So what this means is that whenever we have systems in series like this, or up here, the order of a serial system doesn't matter. Okay, it doesn't matter which one comes first. The last thing we're going to do here in this chapter, or at least in this part of the chapter, is very important because this is where we're going to find a system output, not by using convolution like we did in Chapter 2, but we're going to use the convolution property and use frequency domain methods to find the output of the system. And you know, the nice thing here is that we won't have to do any convolution. So the idea here is that suppose that we're given a system and we're given its input signal or sequence x of n and the impulse response h of n. All right, and our goal is to find the system output for this system. So all we know is what goes in, and we have to know the impulse response of the system, and we can find the output. So what we did, you know, back in Chapter 2, we used convolution to find the result. So if the input was x and this system is described by some impulse response h of n, then the output y of n was equal to the convolution of x and h. And that, remember, in discrete time, convolution is given by this sum, the convolution sum. And you know, we did several examples of this back in Chapter 2. What we're going to do now in this chapter is use Fourier transform method, which is oftentimes simpler. So what you do to do this in the frequency domain is we're going to first find the Fourier transform of x and the Fourier transform of h. which is, remember, that's called the frequency response. So now, using the convolution property, remember if x sub j omega goes into this system, then the output y of j omega is equal to the product of x and h, all right? And these are the Fourier transforms, of course, of x and h. So there's no convolution needed here. Now, again, there's no free lunch. We have to find the Fourier transforms of x and h. We can't just multiply, this x here times this h here, because these are the sequences in the time domain. We have to go to the frequency domain and first find the Fourier transforms. Multiply them together to get the Fourier transform of the output, and then the last step will be to find the inverse Fourier transform of this to get y of n. And formally you could use this integral here, but we're going to do this by inspection. All right, and you'll see in the example that follows. So here is our example for doing this method. So let's say we're given a system, and let's start over here. The system has the following impulse response: 2 times 1/5 to the n times the step function u of n. And we're also told that what goes into the system is the following sequence: x of n is equal to 5 times 2/3 of the n times u of n. And our goal here in this example is to find the system output y of n. All right, so in the time domain, again, we could do this using convolution. X of n, this sequence here, goes in, and the output y of n, which is what we're looking for, is equal to the convolution of this x of n and this h of n, this impulse response given up here. But we hate convolution, right? We don't want to do that. That's like torture. So let's do this in the frequency domain so we don't have to do any convolution. So in the frequency domain, we're going to find the Fourier transform of x to get x of j omega, and the output is going to be equal to, well, I should say the Fourier transform of the output is going to be equal to the Fourier transform of the input, big X, times the frequency response, which is, of course, the Fourier transform of h of n. So our first step here is we're going to find the Fourier transform of x and h. And notice both x and h up here are basically these exponential functions, right? They're a to the n times u of n. And so the transform is 1 over 1 minus a times e to the negative j omega. So if we look at x, we've got a 5 out in front, so we'll put that on top. But our a is just 2/3, so it's 1 minus 2/3 e to the minus j omega. For h, we've got a 2 out in front, so that goes up on top here. And our a value is 1/5, so it's 1 minus 1/5 times e to the minus j omega. All right, so I'm just using this result here and just comparing it to these functions up here and plugging in the value for a. The next thing we can do is we can write the Fourier transform of the output. So y of j omega is just equal to x of j omega times h of j omega. So we take this function here and we multiply it by this function here. That's why we have the 10 on the top. 5 times 2 is 10. And on the bottom we have, this term multiplied by this term, so I put each of those in parentheses. Okay. Now let's go to the next slide. So our next step, our last step, is, we've got this expression for the output transform, y of j omega. All we have to do is find the inverse transform to get y of n. The problem here is that this form here, that y is, big Y is in, we don't have a Fourier transform pair that we can just look up. Okay, so the trick here, and again, we did this in chapter 4, so this should be, the concept is exactly the same. We're going to use partial fraction decomposition to break up this fraction here into 2 pieces. We'll call the first one, we'll give it a coefficient a, uppercase a, and that's this term down here, the 1 minus 2/3 e to the minus j omega. And the second term, we'll call it b, all right? And a and b, of course, are unknown at this time. We have to figure out what those values are, such that when this and this are added together, we get our original here. So how do we figure out what a and b are? Well, the method, and again, if you look this up, there are several methods for doing partial fraction decomposition, but I think by far the fastest and easiest method to determine A and B is the following. Let's say we want to figure out what A is first. So we need to isolate A all by itself. So let's multiply everything, the left side and everything on the right, by whatever's underneath A, 1 minus 2/3 e to the minus j omega. So here's the result, okay? Notice over here, when we multiply by 1 minus 2/3 e to the minus j omega, it cancels this term here. So there will always be cancellation, which is nice. So I have this on the left equals A all by itself, and then of course the B picks up this 1 minus 2/3 e to the minus j omega. So in order to solve for A, we have to make sure this term here, this second term, goes to 0. So when does that happen? Well, it happens when this expression inside these parentheses goes to 0. So let's see what happens here. So we're going to set, we want 1 minus 2/3 e to the minus j omega equals 0. So therefore, 2/3 times e to the minus j omega equals 1, right? Because 1 minus 1, of course, equals 0. So let's solve this for e to the minus j omega, and we get e to the minus j omega equals 3/2. So if we set e to the minus j omega equals 3/2 up here, this term goes to 0, but of course we need to set e to the minus j omega equal to 3/2 here too. So notice down here on the left side I have 10. 1 over 1 minus 1/5 times 3/2. All right, so I've got the, here's the 1/5, and remember e to the minus j omega is equal to 3/2, is equal to A. So 1/5 times 3/2 is 3/10. So A is equal to 10 over 1 minus 3/10, and of course 1 minus 3/10, that's 10/10 minus 3/10, which is 7/10. And so 10 divided by 7/10, remember when you divide by fractions, you multiply by the reciprocal, so we get A is equal to 100 over 7. All right, so there is we're half done here. There's our coefficient for A. To find B, you just do the same method, okay? You're going to multiply everything by, we want to get B all by itself up here. So we multiply everything by 1 minus 1/5 e to the minus j omega. And that will cancel out this term over here. And let's see, we are going to end up with this expression here. And now to get rid of this term here, so that B is all by itself, because we're solving for B now, notice we want 1/5 e to the minus j omega to equal 1. Okay, in other words, e to the minus j omega has to be equal to 5. All right, because notice if e to the minus j omega is equal to 5, we have 1 minus 1/5 times 5, that's 1 minus 1 is 0. And this term, poof, it vanishes, right? All right, so underneath here, we have 1 minus 2/3 times, remember, e to the minus j omega is 5. So we have 1 minus 2/3 times 5. Well, that's 1 minus 10/3, which is negative 7/3, all right? So this is 3/3 minus 10/3 is negative 7/10. I think I might have said that wrong, all right? So 10 divided by negative 7/10, remember, multiply by the reciprocal, and we get negative 100 over 7. Okay, so A is 100 over 7, B is negative 100 over 7. So now I can take these two results that I circled here, substitute them back in for A and B, and here's the 100 over 7, here's the minus sign, which we picked up here, and here's B, which is negative 100 over 7, because there's the minus sign. Let's take out that 100 over 7 out in front, and what's left inside is 1 over 1 minus 2/3 e to the minus j omega, minus 1 over 1 minus 1/5 e to the minus j omega. And again, by using our handy-dandy Fourier transform pair from earlier in this chapter, this is for the exponential functions, we see that in this first term, A is equal to 2/3 down here, and in the second term, A is equal to 1/5. So therefore, when we take the inverse Fourier transform by inspection, y sub n is equal to 100 over 7, that's our coefficient out front. This term here gives us 2/3 to the n. This second term here gives us 1/5 to the n. Remember, there's a minus sign there between them. And then, of course, both of these are multiplied by the step function. So here is the output of this system for that input that was given to us. Now, notice, that this was, of course, there was still a little bit of work. Most of the work was right here in having to do partial fraction decomposition, okay? But, partial fraction decomposition is not that difficult. It's just algebra. There's no calculus. There's no complicated, steps like we had to do when we did convolutions. So this is, believe me, this is a much easier way to do this than by doing convolutions. So that takes us to the end here of part 3 of this chapter's lecture. I will see you shortly for part 4 soon. Goodbye.